topic for this lesson is field effect transistors, or FETs, FETs. The field effect transistor has an extremely high input impedance and a better frequency response than the BJT, the bipolar junction transistor. The small signal gain of an FET, however, is not as high as that of the BJT. The FET, thus, is a good alternative to the BJT in those areas of application where a high input impedance and a better frequency response is required. FETs can also be used as constant current sources and voltage-controlled resistors in certain special applications. The more important areas of FET use are digital circuits and systems. The basic structure of an FET is shown in this figure. The main body of this component is a single, continuous length of N-type semiconductor material. However, there is a small section of P-type material placed on either side of the main N-type section. Both of these small P-type sections are electrically connected. The lead connected to these two sections is the gate. The other two leads, source and drain, are connected to either end of the N-type material piece. The standard symbol for an FET is illustrated. The FET can best be described using an analogy of water flowing through a pipe. A movable valve in the pipe, the gate, controls the flow of water. The FET shown above, although generalized, is the junction FET or JFET. For proper operation, an FET must be biased as shown in the figure. A negative voltage applied to the gate lead causes the PN junction to be reverse biased and consequently produces an electrically charged region within the N-type material. This charged region is called an electrostatic field. The electrostatic field opposes the flow of electrons through the N-type section, acting partially like the partially closed valve in our fluid model. As more negative voltage is applied to the gate, the electrostatic field becomes larger and less current is allowed to pass through the FET to the drain. The current path from the source to the drain is sometimes called the channel. The voltage applied to the gate effectively controls the size, the current capacity, of the channel. FETs operate in a very similar manner to the triode vacuum tube. The gate of an FET corresponds to the tube's grid, controlling the amount of current flow. The source of the FET is equivalent to the tube's cathode, acting as the source of the electron stream through the device. The FET's drain is analogous to the tube's plate. Since the input impedance of FETs are very high, they draw very little current. Thus, they place minimum load on their input source. They can be used in highly sensitive measurement circuits or other applications where loading might be an issue. A P-type JFET is similar to an N-type JFET, except that all polarities are reversed. All the discussion until now has been on the N-type JFET, although any FET will have these generalized properties. The symbol for a P-channel JFET is shown. Parameters used when working with JFETs are shown in this illustration. In the circuit now shown, for V sub GS equal to 0, the value of drain to source voltage V sub DS, at which the drain current I sub D becomes essentially constant, point B on the curve, is called a pinch-off voltage V sub P and has a fixed value for a given JFET. Any further increase in V sub DS produces a constant drain current. The drain to source current with gate shorted, I sub DSS, is the maximum drain current that a JFET can produce at V sub GS equals 0 volts. When the drain current I sub D begins to increase very rapidly without further increase in the drain to source voltage V sub DS, breakdown occurs, point C shown. Pinch-off occurs for V sub DS values less than V sub P when V sub GS is not 0. The off value of V sub GS is given by the device data sheet and is equal to V sub GS, which is equal to minus V sub P. Let's look at an example. For the JFET in this figure, V sub GS, the off value, is equal to minus 7 volts and I sub DSS is equal to 14 milliamps. Determine the minimum value of V sub DD required to put the device in the constant current region of operation. Since the off value of V sub GS is equal to minus 7 volts, V sub P is equal to plus 7 volts. The minimum value for the JFET to be in the constant current region is V sub DS, which is equal to V sub P, and therefore is equal to 7 volts. In the constant current region, with the gate to source voltage V sub GS equal to 0 volts, I sub D is equal to I sub DSS, or 14 milliamps. The drop across the drain resistor, R sub D, is determined by the equation V sub RD is equal to I sub D times R sub D, which is equal to 7.06 volts. Applying Kirchhoff's law around the drain circuit, we get V sub DD equal to V sub DS plus V sub RS, or 14.06 volts. This is the value of biasing voltage connected to the drain V sub DD to make the drain to source voltage V sub DS equal the pinch-off voltage V sub P, and put the device in constant current region.